Yeah, so we continue the session with Tanguy Piero, who will speak about EPOS LHC-R. The stage is yours.
Okay, I keep the title money, but doesn't matter. Okay, so good morning, everybody. My pleasure to be here, and thanks for the accepting my abstract. Yeah. So I will talk about EPOS LHC-R, which is a new version of EPOS LHC. So the R could be like for retune, but actually I like to see LHC and see R, so collect for cosmic ray, because this one is really more dedicated to cosmic ray, where the idea was, remember EPOS LHC is there since 2012, so it's already quite old. And even if it's still very successful at LHC, we learned a lot in between, new data and so on, and it was time, I think, to update it. And in between, there was a work on EPOS 4 that Klaus Werner will show tomorrow. And this is, of course, also has a big influence. I will come back very soon. So my outline, yeah, I will present what was necessary to change, and then impact on Xmax. This I already showed in different conferences, but what is really new and very interesting is that now Core Corona is implemented and updated to LHC data in this version, and we will see what's the impact on the muon production. It's not yet available. It's still preliminary, but it's very close to it. Just to remind you quickly that indeed, I don't know if somebody presented that today, this week, but you know it, you heard about it, that the hadronic shower development depends a lot on very few parameters that you can extract from Heitler model, for instance. And so namely, of course, the mass and the energy of the primary, that's the one thing you want to know, but also the cross-section of the hadronic interaction, inelasticity, multiplicity, and something that was put a bit on the side for a very long time because it's actually very hard to change and in principle very well constrained by a theory, which is the ratio between pi0 and the rest of the other particles. And if you look at this study on the Sibyl, for instance, where you change with fraction of pi0 as function, so you multiply by a few percent or you divide by a few percent, you look at the number of muons, you see that it has an extremely strong effect. So the muon production is very sensitive to these things, much more than any other quantity. So we have to really look into the details of the theory and on the data to try to constrain that as much as possible. So a small summary of what has been updated at LHC in 10 years. So you get a new cross-section from a different experiment. You get high energy data from all the main experiments. You get also detailed proton lead or actually xenon lead, a lot of measurement CMS, but also ALICE had very nice distribution now, which are actually data available since 2 weeks. I couldn't put it in the slide I wanted to, but yeah. Yeah, and of course, particularly as function of multiplicity, you saw a lot already that was presented by Peter Skand, by Alice presentation and so on. And this may have an influence on number of muons. It's what I will show you today. So as I said, we go from EPOS LHC to EPOS LHC-R instead of going directly to EPOS 4, which is public since 1 or 2 years. But the problem is that it's very slow, and it's also not technically possible to run it with air showers in air shower simulation yet. The goal is to be able to do that, but still requires some work. So actually, I took part of the code of EPOS 4, the one which was especially the core corner thing, and the hadronization, the statistical hadronization. And this is part of the new thing in EPOS LHC-R. And I also put like a charm, but only not forward yet, so it has no big influence for the moment. I also put something related to saturation that Klaus will talk about. So it's really try to mimic EPOS 4 as much as possible. That we learned a lot of developing this version. So I wanted to keep this knowledge, but in a simplified way that it's fast enough and also easy to put it for air showers. So it's kind of an approximation of this, but it's based on what was developed for EPOS 4. So what I show today is still preliminary, but it for the first time includes the core corona for air showers. So I will maybe go quick on the first slides because I showed it already. So the plot has been updated with the latest version, but it's the same. So I fit to alpha data. So the cross-section goes, especially the inelastic one, goes a little bit lower than before. So it has an influence for the extrapolation to high energy, but not that much. Actually, what matters more is that for the fluctuation of particles I will show later, I had to introduce, and also for EPOS 4 we did that, you have to introduce the color transparency, which means that the nucleon in the nuclei may, or a nucleon actually, may have fluctuation of structure inside. It means that the cross-section is not constant. It may be a little bit lower or a bit larger, even by event. And because of that, you actually have a change in the cross-section for nuclei, and then you see that you go from the blue line to this purple dot, which is about 10% lower. And this 10% makes a big difference in Xmax, I will show, and it's the main factor. But in fact, it's better compared to, this is Auger data, so it's actually trying to get as close as possible than these low points. I think these points are less reliable than the new Auger points. Yeah. So just to show that I'm not talking about something which doesn't work anymore. So this is a certain TV in a pseudo-rapidity distribution. So the dots again are always this EPOS LHC-R, so it's actually very close to QGZ4. It's a bit lower than EPOS LHC. And for proton lead, as I said, I have to introduce these things which allow us to have more fluctuation. In QGZ, actually, there is already too much fluctuation, so that's a different story. But this might be attributed to also energy conservation in our frame of EPOS, which is not in QGZ. And the CB, you see that it's actually very narrow compared to the other models. So even with simple data, you see differences in the model. Then a big thing, I think, which was waiting for a long time and really pushed by Sergey, that there was a problem in the nuclear fragmentation in EPOS. Indeed, there was a bug, and so I didn't even put the curve here, but there was a large peak here and not enough here. So now it's corrected. Actually, thanks to Sergey, I just take his code, so thanks a lot. You can't complain, it works, it doesn't work. I retune it a little bit differently, so you see that actually I don't allow some things which are allowed in QGZ, but I think it doesn't really matter. So you see it works reasonably well. And this has an impact on the fluctuation of Xmax, I will show. I also introduced, like Sergey will present it, I think, the real pion and pion exchange, and pion exchange to describe this LHCF data. So you see it's actually better here, but I still have a lack of neutrons here, which I didn't have before. So this is something I have to investigate. It's kind of the last thing I really want to, that's why it's not public yet. I want to understand that. Okay, and then with this version, if you compare to previous I showed in UHCR or with ICRC, it's a bit different. There is not much change actually in the multiplicity and elasticity. The real change is in the cross-section. And I could test it easily that indeed these 10 grams I get now in Xmax, so the shower goes deep because the cross-section is lower. The shower can go 10 grams deeper. So it's from the blue line to actually the Sibyl line, so it's almost equivalent to Sibyl. It's really mostly due to the cross-section. So it's a big impact. And the fluctuation are still a bit lower than the others, but only by 1 gram. I think this is well within the uncertainties. Yeah. So out of this, you get actually a higher mean mass if you will compare to Auger data. Okay, then last ICRC, I presented something which I found very interesting on the way. Again, about rho zero, but not only about the rho zero, which goes very forward in NS61. Actually, looking at more data, even the lab data and so on, I found that there is a large uncertainty on the rho production. And the rho are very important because the pions you can produce directly from your string fragmentation, or you can produce rhos and then rhos decay into pions. If you follow the theory which tells you, okay, you should have isospin symmetry, so you should have 1, 1, 1 for pions or for rhos, then you get at the end the same amount of pi plus, pi minus, and pi 0. And indeed, for pions, it would be very hard to change that. But if you allow the fragmentation to go through the rho resonance, the particle has much higher masses. And then this may allow you to have a more some asymmetry between the rho zero production and the rho plus or rho minus production. And if you do so, then you may have exactly what they did in Sibyl artificially, but here it's really at even at lab data, you can check it. You did at the string fragmentation, so it's not energy dependent and so on. It's really just frame fundamental. You can actually allow yourself to have some kind of 20% asymmetry, and this will produce more rho zero, and then at the end more muons. And if you look at the data, in fact, for EPOS, for instance, I had very little rho zeros, very few. I mean, that's also was shown in your plot, I think, yeah. So in fact, this change is a correction to go, I mean, much closer to the data. So these are rho plus, rho minus, I can describe well, and then rho zeros, it's much better than before. Maybe it's a bit too high, I have to say. A better fit will be maybe slightly below, but still it will be asymmetric compared to rho plus, rho minus. And in fact, compared to EPOS LHC, I have less baryons in the EPOS LHC because you show in NH61 data it was too much, so I reduced that, I corrected. Then I lost muons, and then I got back the muons thanks to this. So it's like a game between rho zero and baryons. And it has a different energy spectra, so it's important. What is the time? I don't know. It's like maybe 5 minutes? Yeah, okay. Good. Okay, then you heard about from Peter Skans, very interesting talk on how you produce particles, so this hadronization. And basically, there is two schools or two ways he was talking a bit about. He presented mostly the string fragmentation, so you really go from he explained it very well. You have a color field, and then you produce pairs of quarks or like quarks, and you put the hadrons. And this, you heard about it maybe, that, yeah, we call in the EPOS framework corona because it's outside, it's where you expect to have a very low density of particles. And this has, like, let's say, a high fraction of pi zero, yeah? This depends a bit on how you produce a rho zero, so you can play a little with that, but still you believe it's like let's quote it high. Then you have coagulant plasma and heavy ion collisions, for instance, where you can produce coagulant plasma, and then you have a collective effect, and then you hadronize statistically. So it's a completely different way. You just share your phase space, and because of that, you have much more strange mass production and baryon production. So this is what is accepted very widely for heavy ion collision in lead-lead central collision. And this is what we call core in EPOS, where you expect a lower, it's not less pi zero, it's a lower fraction of pi zero because you have more baryons, more strange particles, so the ratio is lower. So you may expect that to produce more muons and this to produce less muons. But okay, it's clear when you have a peripheral PP, it's clear when you have central lead, but in between, what do you do? And Peter talk a bit about it. So Klaus Werner actually developed this core corona approach a long time ago, so yeah, almost 20 years ago, to describe the evolution of centrality in lead-lead collision or gold-gold collision at the time of V2, many things. And then we found that indeed you can extend it down to PP energy, and it was working very well, much before you get this kind of plot. That's why EPOS LHC has this implement, but in a conservative way where we thought, no, it's there, but it cannot be too low in density of particles because nobody will believe, no one was believing in that. So actually I pushed the effect to start late, but be strong. So the average is correct, but it doesn't describe the data we had later, like 5 years later. Yeah? So the goal now with EPOS 3 and then 4 and now EPOS LHC is actually to fix the fraction of core and corona in a better way that you can describe this data much better. And it's actually very complex. Yeah, Klaus will talk about it in much more details tomorrow. Yeah. Okay, so what's the difference? Now I put that in EPOS LHC. So I tried, so you see this is a blue line to describe this data, lambda and cascades, so it kind of works. Here you see a discrepancy because you're missing the hadronic cascade, the last stage, yeah, where all these particles will disappear. The red one is QGZ, for instance, so it's flat as expected, but it's actually going through the data, and Sibyl is also flat, but a bit low, yeah? And then the difference between EPOS LHC, where you already have this core corona thing, is that at high momentum, so this is a fraction of the secondary energy of the secondary particles, you see that you get mostly core and less and less, mostly corona and less and less core. Now with the new version, because you start at lower density, so you can go also more forward, you see that the core extends much more forward in this region where it's actually very important for air shower development. So what do you get? This is number of muons. We scale by the energy to power to this beta thing for QGZ. So this is QGZ. This is Sibyl or the EPOS LHC. It's basically the same in this plot. Yeah. If you don't have core corona, but you increase the rows, you get the blue line, which is already some kind of 5 to 10% increase. And if you switch on the core, then you get on top of it again 5 to 10%. So altogether, you actually have an increase of 20% of the number of muons in EPOS. And interestingly, if you look at the energy spectra of these muons, you see that, so you start from the green line, EPOS LHC, you switch on, you have more, you replace baryons by rows, basically. And though you don't replace it, but you have less baryons and more rows, and increase the number of muons, but not at very low energy where you expect it, but actually where you have medium energy, let's say, because of the rows instead of the baryons. So that's actually a good point. But when you go to 100 GeV, this counting energy, let's say, you are still very low. And then you switch on the core, I think actually everything shifts up. So you have more low energy, but you also have more high intermediate and high energy. So it's really a scale up. So it's very interesting because this probably also change a bit the attenuation in the atmosphere and things like that, because you have more muons at high energy. Okay, just to conclude, is it enough for the muon puzzle? Indeed, it seems to be. So this is a Z compared to EPOS LHC. So you see that this is without core corona, just a new with the rows, and this is with core corona for proton and for iron. So the first thing is you see that you seem to have, especially for iron, an energy dependence. So that's really interesting also. And for protons, yep, also. Don't have pointer anymore. Okay. And compared to OG data for this Xmax Z and mu, but this is just rescale into EPOS frame. So Z0 is proton for EPOS LHC, 1 is iron for EPOS LHC, as you can see. And okay, so I think you have to change the battery of this thing. Yeah, no battery. Yeah. But okay, you can see that we reach 1 sigma of OG, and so you may guess maybe it's too many at low energy because you saw the ice top data or cascaded data. So this has to be tested. I mean, this is really new thing. So that's why it's preliminary. So it's really a good sign. But okay, we will see if it's confirmed in the future. And yeah, okay. Okay, so arrive to my summary. So in 10 years, we had really a lot of new data from NA61, from OG, from LHC, and this has to be included in the model. So it's, I think, all we do now. I mean, Sergey with this new version of QGJet also have a new version. And at least in my case, this has a significant impact on Xmax. So this will make your cosmic ray look heavier than what was the case with EPOS LHC. This reduces already a little bit the muon puzzle. Then, if you take into account the fact that you have this rho zero resonances in NA61, but also at other data, then you may get already more muons like this. This has quite some freedom because the data are very sparse, so you can kind of tune a bit like you want here, which is maybe a problem, depends how you see it. And on top of it, you really have to take into account this core corona, I think, this strangeness enhancement observed at LHC, because if you believe our approach in the core corona, I think in EPOS, which describe very well a lot of data, then it goes very forward and it has an impact on the muon production, and a very significant impact. And if you combine these three things, it seems that actually you can reduce the muon puzzle to nothing. Yeah? But still, things has to be done, to be confirmed, but it's really, really a good sign that it's finally could be of which to have a model which describe everything consistently. Let's try at low energy. This is something we try now because Xmax is deeper, so this change also the electromagnetic ground. So this may change the picture also because very often all this low energy experiment rely on the ratio between muons and electrons, not just on the absolute value. So stay tuned. I really hope, I mean, my goal now is to release it before UHCR, maybe before enough that people can do a library or something and test it. And then the next step will be to put all these new things also in EPOS 4, which part of it are not there, to have a complete picture. But well, I think this will take some years, so I wanted to finish first this to have something usable. Thank you.
Thank you for the informative talk. Now, questions?
Thanks.
Yeah, it's working.
Yes, it's on. Thanks a lot, Tanguy. This is very nice, and I hope you really release the model finally. Yeah.
I'm motivated now.
No, we have all heard you, and
Yeah.
so you will be stoned if you don't do it. No, but the other thing is, aren't you working really towards having more muons all the time? Isn't there a bias? Let's assume in the end it turns out it's not more muons that we need.
Yeah.
But of course, we all are sort of primed towards looking into effects that increase the muons.
Yes. So it's true. There is a
So
bias.
there's a certain danger that we just go the wrong direction, right?
Yeah, it's true. There is a bias. And actually for this version, I kind of want to follow this bias to see, okay, how far can we go? And does it, so it's not free of thinking about air showers. I think with EPOS 4, it will be a bit different because there's much more constraint from LHC and so on. So I think we will be, let's say, more, what to say, bias free.
Yeah.
But this version is a bit like Sibyl Star. Like we want to have more muons. I want to have more muons, yeah. But it's compatible with all the data. I have nowhere a sign of being crazy. So maybe the rho zero is a bit high, so I can go down a little bit. This kind of thing, this kind of thing I want to check. But indeed, this EPOS LHC air because cosmic ray plays a role in the tuning.
Yeah. Okay. Yeah.
I assume it. But there was a
question online. Okay, just go in.
Yes. Yes, who is? Can you hear me?
Please. Hi.
Okay. Thank you very much for your talk. It's really fascinating to follow the evolution of the EPOS model. I just wanted to comment a little bit on the rho zero enhancement on the string fragmentation basis. So I've been actually working with that recently. I really regret that I couldn't make it in time to prepare the contribution for this conference. But what is interesting about the raw meson production from strings is that it seems that two points are very important for that. And first one is the criteria that is used to select the breakpoint of the string. So usually the models, they adjust the breakpoints so that the mass of the string match the mass of the hadron. But if you actually force the breakpoints not to match these criteria exactly, but in a certain range of tolerance, then the production of higher particles is favored. And also what can influence the raw production from the strings is total angular momentum conservation. And because it seems that for vector particles, it is easier to conserve the angular momentum if you include the spin of the strings that you can calculate. So it is easier for vector particles to satisfy the angular momentum conservation than for the scalar particles. And interestingly, a very interesting result was that when I tested this hypothesis in a simple program code that I wrote, it turned out that in the end that the fraction of rho zeros was higher than for charged rho mesons. So it got around 14 to 16% enhancement for rho zeros just due to these small modifications to the string fragmentation scheme. So maybe if you would consider this to be interesting, I could contact you maybe and like send you some results because I think this is what might be useful from the side of the theory to describe why we should enhance row zeros, but do not enhance charged row mesons.
Yeah, thanks a lot. Actually, yeah, it's very interesting. Yeah, yes, you can contact me. Actually, this mass range is exactly what I use to increase the row zero in the strings, but I don't have the spin. So if you have actually these things in as a theoretical constraint or justification, that's very nice. Yeah, thanks a lot. Yeah.
Okay, thank you.
Okay. More questions, comments? No. Okay. Actually, I do have a comment on the same subject.
Yeah.
And I would say that a strong violation of isospin symmetry is forbidden by law.
Exactly. But I guess
Let me just finish.
Yeah.
One can check textbooks, one can check just Wikipedia page. It's established at a very fundamental level with lattice calculation. So if one wants really deep insight, there was a recent dedicated workshop at the University of Mainz. I just invite anyone to check the material.
No, exactly. So it's you notice the difference with the ICRC. I removed isospin breaking here. I put mass. It's just maybe like what the previous speaker said, that it's maybe a different mechanism than isospin breaking. What I wanted to say, putting isospin, no, it's not on this slide, it's on the slide on here, is that the model used that, as you say, as a law to constrain it. And we always were bound to that. And I think that's why the muon puzzle stayed so long, is because we thought, we can't change that. But maybe not for isospin breaking reason, but for something like the spin thing or momentum conservation or whatever, there is a production of more zero compared to charge rounds. And then this really allows to have a different number of muons. But it's not, I'm not saying that you saw, there is no isospin violation anymore in my slides. I took into account your comments last time. So it's it may be a different mechanism, but at the end of the day, it's really explaining why before we were bound to this very strong low pi zero fraction, and then because of Corona, which is a different way of changing the ratio, and this maybe mechanism in the string fragmentation, we may have more muons. Yeah.
Just to this, even if you do thermodynamics, you still have to agree with lattice.
Yeah. So in the statistical decay, you have same amount of pi zero, pi plus, pi minus. This is not violated, but you have more baryons, you have more strangeness, and this changes the ratio of pi zero to the rest. So it doesn't break isospin symmetry. Yeah. Actually,
may I add a little bit to that on the isospin conservation. So actually, the increase of row zero does not necessarily imply the isospin breaking, because when you consider the isospin conservation, you should also consider the spin for higher resonances, because row zeros are not only produced directly from strings, they also produced from the decays of heavier resonances like row 1700. And you also need to consider that in the decays of this resonance, you do not necessarily get 1-to-1-to-1 ratio for the row mesons.
That's true.
Yeah. Good. So we agree.
If no more questions, we thank time. Doubt will report investigating muon content in extensive showers with PCR. We are looking forward.
Do I get a pointer though? Because it would be great.